Okay, so we're at our final talk for the workshop, and we have Felix Parraud from Stockholm going to tell us about the free energy of matrix models.
Thank you for the introduction, and thank you for giving me the opportunity to talk here. So, as you just said, today I'm going to focus on the so-called matrix models and the link with free probability. I'm going to give a few applications to free entropy and map enumeration stuff. But to begin with, let me actually define what are those so-called matrix models. So basically, maybe I should try to. Yeah. Our main object of interest will be the following. The random matrix model, which has the following density. So you take dp of y, where y is a d-tuple, and you say that this measure must have the following density: exponential minus n times the non-renormalized trace of w of y times dy1 dyd. So let me define every notation I have here. Oh, and of course, let's add in a renormalizing constant to make sure that this is indeed the probability density. And here I picked W, a non-competitive polynomial. And dy is just a Lebesgue measure on the set of Hermitian matrices of size n. On Hn of C. This will be Hermitian matrices of size n. So you might wonder, what is so interesting about this type of matrix models? Well, there is a link with free probability which comes rather naturally, and which comes from the fact that basically at infinity, those random matrices will behave like free operators. Well, no, not like free operators, but like operators whose conjugate system it's basically given by the differentials of this polynomial W. So basically, let me summarize that with the following proposition. Under some assumption of W, because obviously, well, you need some basic assumption like this thing should be actually integrable. So typically you want W to be convex, for example. That usually gives you good enough assumptions. So under some assumption, the family Yn, which is basically the one with the density that I defined above, converges in star distribution. Towards a family of operators that I will just denote by Y. Towards Y, and which is a d-tuple, so Y1, YD. All right, and so what does it mean exactly to converge in star distribution? Well, basically it means that the trace of any polynomial evaluated in Yn will converge towards the trace of the same polynomial but evaluated in Y. So basically, you get that for any polynomial P, 1 over n times the trace of P of Yn is converging almost surely when n goes to infinity towards the trace of P of Y. And so what is actually interesting about this thing is the description that is given of the limit. Basically, the trace of like Y will satisfy the following equation. for any polynomial p, you get that the trace of p of y times the non-commutative derivative, well, the cyclic derivative of w with respect to the ith variable evaluated in y. This thing is equal to trace tensor trace of the non-commutative derivative or differential with respect to the ith variable of p evaluated in y. And so basically, what does this thing means? It means that, oh, is this, oh, okay, maybe I shouldn't write so low here. All right. I won't go any lower then. Not this one, unfortunately, only this one. Can I? Oh, that's the one. All right. I will keep that in mind for the next. Anyway, so what this means is that as a consequence, the family cyclic derivative of w evaluated in y for y between 1 and d is a conjugate system for y. So basically, as n goes to infinity, those operators will let you deduce some properties on this type of free operators. All right, so maybe I should give a few very basic examples as to what is that thing, like for some given potentials. And notably, I think it's important to at least give the most well-known example, which is the case where W is equal to 1/2 sum for I going from 1 to D of yi squared over 2. No, sorry, I already wrote the 1/2. Then in that case, well, you get that, no, wrong colors. You get that the differential, well, the cyclic differential with respect to I of W evaluated in y, well, this is simply yi. So basically, you get that the conjugate system of y is y, and basically that those are free semicircular variables. And similarly, you also have that if you take a look at this density, then this is very clearly the density of a d-tuple of independent GUE random matrices. And so basically, the most simple example you can think of is the case where you have the law of a d-tuple of independent GUE matrices, and then at infinity it behaves like a d-tuple of free semicircular variables. So let me write that a bit. Yn is a d-tuple of IID GUE. Y is a free semicircular system. Okay, so that's the most simple example that you can think of, but basically starting from there, every other potential is not quite as easy to work with, because in the case where you have GUE random matrices, then basically you know that every coefficient is just an independent GUE random variable up to symmetry, but that nice description of the entries is basically lost as soon as W is not just a quadratic potential. Like from there on, you cannot assume that the entries are independent, for example, that completely disappear. So let me try to grab that. So basically, how do we usually proceed to prove this type of proposition? So what people usually do is basically a proof in 3 steps. Maybe I should rename the proposition, like, will be star. Well, proof is a big word, but so first, you use some sort of integration by part, or like change a variable. You use some sort of like analytic properties of the density P to deduce some sort of equation which will be satisfied by your system. So usually name those equations Schwinger-Dyson equation, basically. An example of them. And so let's say by integration by parts, you get that the expectation of, I will write tau n for the renormalized trace of the cyclic derivative of W evaluated in yn times polynomial evaluated in yn is going to be equal to the expectation of the trace tensorized with itself of the cyclic derivative of P evaluated in yn. So basically, you get what I wrote here, but at finite time n, not at infinity. So that's the first step. This one is usually verified for like pretty much any polynomial W. You might want to check a few integration properties on W, but this is usually pretty lenient on the assumption that you need to make on W. The second step, though, is more tricky. And this is usually where you have to really restrict what kind of potential you're studying. So you want to use some sort of concentration estimate to basically deduce that this thing is not only true for like the expectation, but also almost surely, up to, of course, some error term, like some big O of 1 over n, something like that. But really, you want that to happen you want to get rid of the expectation, because here you have like when you're still at this step, you have an expectation of a trace, and then here you have an expectation of a product of trace. So it doesn't fit very well if for your computations, because you want to have basically, it would be okay if, for example, we had an expectation of trace tensorized with an expectation of trace, but that's not the case. So let's say that instead you have some concentration estimate and you deduce the followings, but without the expectation. So let me rewrite it. Cool. Plus some error term like 1 over n. Usually you don't need it to be 1 over n exactly, but let's say it is like that. Well, now once you're there, basically you have that your non-commutative random variable yn are satisfying those equations for any I and for any polynomial p. And as you can see, this is basically this one, but at times n, so with the correction terms. And so the next step usually is to try to show that basically if you have a system, like if you have a d-tuple of operators which satisfies this type of equations, then basically you have a unique solutions. And since you have a unique solutions to this type of equations, and that the operator yn are satisfying those equations up to an error term of order 1 over n, then you deduce that when n goes to infinity, then those traces will always converge towards those. So there you need some sort of like, you need to show that basically those things have like a unique solutions, which is actually quite tricky to do. Like this is usually the step where you have to restrict yourself to something like a perturbation of the quadratic potential. All right, so let me write it down. Show that I will write that, I will name that E. E has a unique solution. All right. So this is how like people usually study this type of matrix models. That being said, yes? This one is an exact equation. And usually what you do is that you study this thing. So maybe this minus this thing. All right, you study this minus this, and you forget about the error term for a second. And you know that the expectation of that thing will be equal to 0 thanks to this. And then you use your concentration properties to just say, well, since this minus this thing has to concentrate, well, and that this thing is equal to 0, you get that this thing has to be close from something smaller. All right. So you can actually go, like, I've given you like a very small introduction. You can get more out of all of those strategy. Yes? Yes. Basically, if y is such that for any polynomial and any I between 1 and d, this is always satisfied, then the distribution of y is always going to be the same. And it exists, actually. That's also something that is non-trivial to show.
Is that like some kind of, in free independence is saying there's a universal rule that all these polynomials have to satisfy? Is that comes to the same thing? Like Freenet says there's a way of computing mixed things, knowing individual things, because there's a universal rule for putting the individual things together.
It is, yeah, it is pretty similar. The one major difference is that the y1, y2, and so on are not usually freely independent when they satisfy this type of equations. Yes. Yeah. It's just a bit tricky because when you have like some sort of freeness equations, then what is quite nice is that basically when you want to compute the mixed moment, you can do it by induction on the degree of your mixed moment. But here, well, you can't really proceed like that because even though this part you have like that the degree of p is like smaller, while this part you have like you have this dy this differential of w, and the differential of w can be like of degree way higher, which is quite problematic. Like the one case where like it's not a problem is when w is degree 2, and then you just get that this is xi, and then you can do the usual Schwinger-Dozen equation for the free semicircular system, but not in all generality. And the way that people usually study that in all generality is that they look at like the sum of a exponent n. Well, that's how you show the unicity, but well, you can build an explicit solution by using some sort of like map enumeration method, or you can also do the strategy that I will explain to you during that talk, which is new. All right, so it's okay. So let me now talk about our approach. So there, we're going to define a few. Let's define a few quantities. So first, xn is a d-tuple of independent GUE. Secondly, you get that x is a free semicircular system. A system of a free semicircular system. Semicircular system. V is basically a non-commutative polynomial which satisfies some nice assumption, which I will not detail into that talk because that's those are mostly technical assumptions. Is a nice non-commutative polynomial. And then you define xtn, which is basically an interpolation between x and xn. So the way we do it is like the heuristic behind that is that you want to basically pick an Horstein-Uhlenbeck process which is starting in your in your random matrix. The way we do it is that we use the fact that we avoid doing any stochastic calculus, and we just use the fact that the marginal of such an Horstein-Uhlenbeck process has like a given law in terms of like you have an explicit law in terms of the law, the process at time 0 at times infinity. And so basically you end up just defining that xtn is equal to exponential minus t over 2 times the initial times xn plus the square root of 1 minus exponential minus t times x. I will explain later why exactly this is so important that we pick such an interpolation, basically. All right, so then you want to study the expectation of the trace, the renormalized trace of P of xn. So xn is GUE random matrix times the exponential, a d-tuple of GUE random matrices, minus n times the non-renormalized trace evaluated in V of xn. Okay, and what I say is that oh yeah, thanks. And so now the heuristic behind all of those computations is that okay, we have this term which is obviously going to like change the law of xn. Like this is obviously going to like completely like this will make your computations way harder. But the point is that like if you forget about this, then you just have the trace of a polynomial evaluated in GUEs. And the trace of a polynomial evaluated in GUEs, we know that at infinity, it will behave like the trace of the same polynomial evaluated in a free semicircular system. So, okay, we just subtract these quantities. So the trace at infinity of P of x minus, well, this term, since now this term is still lying around. So the expectation of exponential minus n times the trace of V of xn. All right, so we can write that down, and that gives us the expectation of minus the integral from 0 to infinity, because this is basically the times infinity and times 0, so that's why we have a minus sign, times the differential over t of the trace. I will use the same notations, but this time this is the trace on that thing, well, on that space where both mn of c and x lives, of p evaluated in xtn times, once again, this exponential. And so once you're there, you can basically just compute this thing, and the differential of a polynomial evaluating something which depends on t, it's basically just the non-commutative differential of that polynomial hash the differential of xtn. So that gives you the integral from 0 to infinity, let's keep the minus, times the expectation of the trace of the differential of p. So all right, I assume we had like a d-tuple, so it should be a sum over I. Where do I write it? Here. Sum over I going from 1 to d of the differential with respect to the ith variable of p, evaluating xtn, hash this differential over t of x itn, all right, times this exponential. And once again, this is pretty straightforward to compute, because this thing well, the dependency is fully explicit. So that gives us minus the integral from 0 to infinity of the sum for I going from 1 to d of the expectation of the trace of the differential of p sharp exponential minus t over 2 and then there's a minus times xn plus 1 minus exponential minus t exponent minus 1/2 times exponential minus t times x. All right. And we're getting a bit, the computations are getting a bit out of hand. So now that we are there, what happens basically? Well, on one side, we want to like estimate this thing. So what do? We end up with like the trace of a polynomial, and we have this variable x, well, xi. And so you end up with like the trace of a polynomial times xi. So then you want to use Schwinger-Dyson equation to show that this thing is just the trace tensor trace of the differential of your polynomial. On the other side, you have this xin. And then what you want to do is to use Gaussian integration by parts, or basically to do some sort of like, if you're not familiar with that, some sort of like finite n Schwinger-Dyson equation, which would let you like differentiate the rest of your expression with respect to xn. But then what happens is that here, well, of course, when differentiated with respect to xn, you're going to differentiate that part. And that part will somehow simplify with the one that comes out of xi, like the Schwinger-Dyson equations at infinity. But then you're also going to differentiate this thing. And while differentiating this thing, you will basically have some sort of covariance term which appears. So I'm skipping any other kind of computations to basically just say that when doing so, you will end up with the following expression. Some expectation of the trace of well, first, like the covariance term between xn and this exponential. So grad, I usually denote that by like nabla v of p. And then you also have the term which appears from like xi interacting with that one, and well, xi interacting with that one, and xi also interacting with that one. But here what happens is that those two terms will somehow simplify each other, and it is kind of miraculous, but you can fully compute everything, and you will end up with some small term, some term for the 1 over n square times an operator L, which acts on P. And all of that has to be evaluated in xn. Yes. Trace of v of xn. So even for the case where like v is equal to 0, so where basically you do not have this, and then you just have the expectation of the trace of a polynomial in GOEs, then the fact that you have this operator L multiplied by 1 over n square is actually quite strong. Like this basically immediately yields the strong convergence of a family of independent GOEs towards a family of free semicircular. So the result of Heigrove and Thompson from like 2006, I think. And you can really deduce like quite a few things out of that. Like you can actually go a bit further and show that like the norm of like your polynomial in xn is actually 1 over square root of n closed from the norm of p of x. You can deduce some concentration estimates. You can really like do quite a few things, but the point is that like this is not really like what I want to study like during that talk. I really want to study the case where v is not equal to 0, so where we are not in the case of GOEs. And then what happened here is that we somehow have proved some some form of closed equation loop, because we started from the expectation of the trace of P, and we end up with the expectation of the trace of an operator evaluated on P. So we can somehow send that back on the other side, and this will yield the following equation. The expectation of the trace of identity minus nabla v minus 1 over n square L evaluated in P, which is then evaluated in xn, times this exponential minus n trace of v of xn is equal to the trace of p of x, where x is a family of free semicircular, times this expectation. So times the expectation of exponential minus n trace of v of xn. And then, well, it is a bit weird to have this expectation here, but what happens is that once you divide by this is basically the renormalizing constant of of the density that I define here. There. So what we will do from now on is to define the following densities: dp of yn to be equal to exponential minus n trace of lambda v, where lambda is a scalar, of yn. So I guess we can take the lambda out if it's a scalar. Times d mu n of y1n, and so on, ydn, times a renormalizing constant. But this renormalizing constant is basically the one I've wrote over there. So expectation exponential minus n lambda trace of v of xn, where this mu n means that the law of yin has to be the one of a GUE. Mu n is the law of GUE of size n. And so basically what we got over there, if we just go back to that very last line, is the fact that the expectation of the trace of identity minus nabla v, well, nabla lambda v, but what happens is that this nabla is like linear with respect to v. So nabla of lambda v is equal to lambda of nabla v. So lambda times this thing, here we write it, lambda times this nabla, minus 1 over n square times L, evaluated in P, then evaluated in Yn, but this thing is equal to the trace of P of x. And so basically that this operator is somehow acting on your random matrices and somehow acting like under the expectation and the trace. I mean, it's basically sending your random matrices to like the algebra generated by X, somehow doing some kind of isomorphism. I didn't dig that much deeper into it, but heuristically what you want to do is, since what you're interested in is the trace of P and not the trace of that operator evaluated in P, is to basically invert that operator. And so heuristically what you want is to write the following, that the expectation of the trace of P of Yn is equal to the trace of the invert of that operator. So identity minus lambda nabla v minus 1 over n square L exponent minus 1 of p evaluated in x. So that would, of course, like fully compute that thing completely explicitly. But in practice, it's impossible to do so. Because, of course, if you take lambda equals 0, then you have the case of the GUI, and then this will work because the operator L is nilpotent. But in practice, it will never be the case. I mean, I haven't shown that, but I would be extremely surprised if you could actually invert that operator for lambda different from 0. L does not depend on large n, which is, it depends, the large L, no, it doesn't depend on V. It's something which is universal in a way. It's, I guess I would have much to say about that because, well, all right. Basically, the operator L is something which appears in a lot of asymptotic expansion, whether it be like Haruntaris, GUI, Q-Gaussian, matrix models. It's kind of always the same operator L which appears when you're studying the next order of your expansion. And of course, you have to adapt slightly the definition, but it's almost always the same. So there is something universal behind that, which I would love to get more information about. But it is still not quite clear to me like where it comes from. But if you, yes, it's the same L. Yeah, it's that L actually. It's basically, this one is the same L as in the case of the GUI. Yeah. Well, okay, in that case, it's the same, but in some other, like typically if you switch from GUIs to like, to, for example, Harunitary, then it will be extremely similar, but it's not exactly the same kind of non-commutative differential. You have to adapt your non-commutative differential from the Hermitian case, like the self-adjoint case, to the unitary case. So, you know, instead of taking like differential of xi to be 1 and so on, you take differential of xi to be xi and so on. And you also have to take differential of xi star. Or like, well, they are like, it's just that like the way you write the operator is extremely similar. Like all you have to do is basically to change your non-commutative differential. All right. The right-hand side? Or, yes. But it is like a 1 over n square expansion. It's not just 1 over n. Okay. Yes. L is like universal. It doesn't depend on V. But all right. So the thing is, this operator is not like, it's not actually invertible. What, however, will be true, and this is something which is not trivial at all, is the fact that if you forget about L, then that thing will basically be invertible in the sense which is not quite clear, because it isn't exactly invertible as like an L2 operator. It's invertible as an operator on the set of polynomial, but then again, you need to like have the, well, anyway, technical details. But the point is that like what you get is the following theorem. So if V is a self-adjoint polynomial, self-adjoint being quite important, because if it isn't a self-adjoint, it means that like the conjugate of the trace of V, which is equal to the trace of V star. So the conjugate of the trace of V will not be equal to the trace of V, and then you don't even have like you don't even have a probability density, since your density is not real. But it's also a topic of interest, but beyond the scope of that talk. So you take V as self-adjoint polynomial, which satisfies some technical assumption. So basically, you want V to be kind of a perturbation of the quadratic potential. It is kind of needed to invert that operator identity minus lambda nabla V. Lambda sufficiently small. Then you get that for any n, the expectation of this thing, the trace of P of yn, is equal to the sum for n going from 0 to k. So maybe for any k sounds like a more reasonable assumption, of alpha nv of lambda p. So this is a deterministic constant which does not depend on large n, divided by 2n, plus some remainder, some error term of order n exponent minus 2k plus 1. So you can do that for like any k. You could even take k which depend on large n, something like square root of large n, probably n exponent, but you can go further, like n exponent 2/3, maybe even n squared, but then you get problem with the concentration and stuff. So, all right. And what is quite nice about this is that like you have a fully explicit version of those alpha nv. You get that, and I should probably move on to different slide, a different blackboard to avoid any issue. You get that alpha n v of lambda p is basically equal to the Taylor expansion of that thing with respect to 1 over n squared. So that is the trace of identity minus lambda nabla v exponent minus 1 times L times this thing, identity minus lambda v exponent minus 1, lambda nabla v, exponent small n, evaluated in P, evaluated in X. So even though that thing is not true in the sense that you cannot invert that operator, if you look at this operator as like something like 1 minus a exponent minus 1, and you do some sort of expansion with respect to a, then it will still be true. You will still get some sort of like a Taylor estimate. All right. Finally, maybe I will not write it because this is a bit, I can gain a bit of time. But basically, here we need some assumption on the polynomial V. We need some technical assumptions which are typically some sort of concentration estimate. You want that like the expectation of the trace of yn exponent k doesn't grow too fast with respect to k. So you don't actually need that, in the sense that if you take the very same density which I defined there, this dp, but you add in a cutoff, so you assume that the norm of, like you basically add that the indicator function that for any I, the norm of, like the operator norm of yin is bounded by k, then you have like the very same theorem. You get like the very same theorem, but you don't need to assume any technical assumption on the polynomial V. But you still need to assume that lambda is sufficiently small, so that like identity minus lambda nabla V is still invertible. All right. So one consequence of this, which is almost immediate, so I guess I will do a little bit of computation, is the fact is, if you're interested in like the expectation of exponential minus lambda n times the non-renormalized trace of v of xn, so xn is, as I wrote there, the tuple of GUEs, and you can basically compute that quantity. So why is that? Well, if you look at the differential with respect to lambda, that basically gives you, well, you just differentiate under the expectation, and you get minus n squared times the expectation of the renormalized trace of v of xn times this exponential minus n trace v of xn. All right? But then, if you take a look at this thing and you renormalize, sorry? No, because you differentiate with respect to lambda. This one, yes, sure, yeah, indeed, thanks. So if you take a look at this thing, well, once again, if you take you look at this density, well, if you renormalize by the expectation of this thing, well, this is just the density of yn. So what this means is that you get minus n squared times the expectation of the trace of v of yn, trace of v of yn, times the expectation of this exponential, because this is your renormalizing constant. V of xn. All right? And you now have a very basic differential equation with respect to lambda. And out of that, you deduce that the logarithm of this thing well, the differential with respect to lambda of the logarithm of this thing, exponential minus lambda n trace of v of xn, is equal to minus n squared times this expectation. But this expectation is something that we computed right here. And so basically, this is just alpha 0 v of lambda p, well, sorry, of lambda v, because this time we evaluate it in v, plus some term of smaller order, so large O of n minus 2. Let's just write it like that. And you could push the expansion, of course, to any order, but this is good enough as it is for what I will explain next. The whole point of that being that you know that this thing behaves like you know how these things behave. And out of that, you can deduce rather like in like a 10-line computation, you can compute the free entropy of this linear functional, basically, alpha 0 v lambda of a polynomial. So that brings me to my next part. That if V satisfies some sort of concentration estimate, then you can basically compute the free entropy of that alpha 0 lambda V. If V satisfies some concentration estimate, then for lambda sufficiently small, you get that the free entropy of alpha 0 v lambda dot, where dot just means that like this thing is the map which take a polynomial p and gives you alpha 0 v lambda p, then that thing is equal to something fully explicit, which is the integral from 0 to lambda of s times d over ds of alpha 0 v s v ds. Okay, so here by free entropy, what I mean is a definition which is almost the same as the one given by Voiculescu, but instead of taking the measure with respect to the Lebesgue integral, we take the measure with respect to the quadratic potential, the GUIs. Why? Because this fits in better with our computations. And in practice, if you want to, like the difference between the two definitions is just a quadratic term that you can fully compute anyway. So it's not, it is not that important. But what is nice is that this thing, this alpha 0 v SV, well, it has like, okay, it has definitions which I've wrote above. So this thing is simply the trace of identity minus lambda, well, minus s nabla v exponent minus 1 of v evaluated in x. And so when differentiating with respect to s, you basically get just, well, two of those things. But what what I wonder is that we get that this free entropy is basically just is linked to kind of like the spectrum of that operator. So unfortunately, this operator is not well defined as like an operator in a Hilbert space. So it's not really like you cannot really define a notion of spectrum. But if someone could make sense of that, that could be quite interesting. Like in a way, like the only reason why this finite entropy is finite is because we can find some antecedent of v with respect to that operator. So there are some link to be made here, which I wish someone could tell me more about, but it's up to you. All right. So another consequence of those expansion stuff is that since we actually have already a literature on the theory of expansion, of topological expansion for this kind of like potential, well, it's quite easy to just look at the two expansion, associate them, and be like, okay, well, we have two expansions of the same quantities, so their coefficients have to match. And out of that, you deduce that basically your alpha 0 v lambda p is basically, it is equal to like some sort of like power series whose coefficients are given by map enumeration method. And so that gives you like a way to count maps just out of like this operator nabla v and L. So more precisely, what I mean is that if you define the following quantity, m g q1 k1 q m km as the number of maps with ki of maps of genus G and with ki vertices of type Qi, which is something that I'm a bit short on time to fully explain what this means. But as an example, if I want to like count m0 of x square 1, x, y, x 2, then what I do is that like I have three vertices, 1, 2, 3. One of them is of type x squared, so that means that we have two half edges coming out of that vertices, and they are both of color x. So one like that, one like that. And then I have like two vertices of type xyx. So two half edges are of type x, and the third one has to be of type y. So I will use different color for that one, red. And this one is the same thing. One half edge is of type y, two of type x. And then I want to basically count the number of map of genus 0 that I can draw with this type of condition imposed. So for example, there are like multiple ways of counting map in map enumeration, which is something I discovered while doing this project. But typically, you want to just link edges, so something like that. You want them connected, yes. It's important that they be connected. You never count non-connected map, which is something I should add in the definition. But the full definition is like, it's quite long. So in the context of that talk, I would rather keep it as short as possible. And basically what you get is that if you define your potential as like some sort of like linear combination of the Qi, well, the coefficient of your alpha 0 v will be fully explicit, and they will be given not only by the enumeration, like the formula here, but also by a map enumeration formula. So what you get is the following. If v is equal to the sum for j going from 1 to m of tj qj, then alpha g v lambda large q0 is equal to the sum over all of the ki going from 1 to m, well, k1 until km integer number, times minus lambda t1 exponent k1 minus lambda tm exponent km, renormalized by k1 factorial all the way until km factorial, times precisely this quantity with the added q0. So times mg of q0 1 q1 k1 and so on until qm km. So a little bit painful to write, but that basically gives you like a fully explicit expression of the mg of all of the qi. And what you should remember out of what I wrote here is that if you want to compute that thing, it will basically be given by the operator nabla qi and the operator L. Like you will have a formula where you apply the operator L g times, and you apply every nabla qi ki times, and that will yields you these quantities. All right, so thank you for your attention, and I will stop here.